Okay, so let's continue with the section B of part 6. Okay, so we are still in part 6, called the reduced echelon form. Reduced echelon form. And we are in section B. Okay, that we are going to call the linear combination lemma. Okay, the linear combination lemma. And this is very interesting lemma, you will see shortly. Okay, so what does that lemma or this lemma say? Okay, so the lemma says the following. So this is the lemma of the linear combination. So linear combination lemma. It says the following. It says that a linear combination of linear combinations is a linear combination. And this lemma is the foundation of the next chapter or the rest of linear algebra when we are talking about linear structures or vector spaces. That means we can take linear combination of those structures and still stay in the space. Okay, so if we take the linear combination of the structures we will see in the next chapter, we will still get the same or the structure of the same space. Okay, so this is a very insightful lemma, very profound and beautiful. Okay, this is the foundation of linear space or vector spaces. Okay, so it says a linear combination of linear combinations is a linear combination. Okay, this is very easy to prove. Okay, you just take the linear combination of some linear combinations and you will see easily that you will have a linear combination of the same structures. Okay, so number 2, corollary says the following. Where one matrix reduces to another, each row of the second is a linear combination of the rows of the first. You can easily prove this one too with a small example you can see. So let me write it down. Where one matrix reduces to another, each row of the second is a linear combination of the rows of the first. Okay, so let's continue. A very simple corollary to prove. Let's have a look at another lemma. So in echelon form matrix, no, this is another of my favorite lemmas. So it says in echelon form matrix, no non-zero row is a linear combination of the other non-zero rows. If you can see the power of this lemma, you recall when we were performing Gauss's method and elementary reduction operations. We take we perform Gauss's method or Gauss jargon by taking linear combinations of rows. Then this lemma is telling us that at the end, the matrix we have the rows of that matrix are not linear combinations of other rows. Okay, so basically by taking the linear combinations of the original matrix, we end up with a matrix in which we have removed or the final we end up with a matrix with rows being linearly independent. If you see, they are not a combination of each other. Very, very beautiful lemma. Let me write it down. In an echelon form matrix, no non-zero row is a linear combination of other non-zero rows. So we have removed linear independence among the rows by performing Gauss's method or elementary reduction operations. Okay, so let me go to next concept. So here, let me give you a definition here. Definition. Definition says two matrices that are interreducible by elementary row operations are row equivalent. Okay, so we have two matrices that are interreducible by elementary row operations are row equivalent. Row equivalent. Very important as well. Okay, so number 5, let's have a look at the following theorem. Theorem says, okay, each matrix is row equivalent to a unique reduced echelon form, and this theorem is very important. Is important to the tutorial we will be doing next. Basically, when you are asked to prove or to say whether two or more matrices are row equivalent, okay, what do? You get the reduced echelon form and you compare them, because if they are row equivalent, they should be reduced to the same reduced echelon form. Okay, so let me write it down. Each matrix is a row equivalent to a unique reduced echelon form matrix. Okay. Number 6. Corollary. We have, okay, so if from a starting linear system we derive by Gauss's method two different echelon form systems, then the two have the same free variables, of course. Very easy. If from a starting linear system we derive by Gauss method two different echelon form systems. Okay, then the two have the same free variable. Have the same free variables. Okay, so I'm going to stop here, and in the next video we will do the tutorial, okay, about proving if two matrices are row equivalent or not. Okay, thanks.